Welcome to the deep dive. Today we're tackling lesson 10, intersected lines. And we know what you're looking for, concrete examples, stuff you can actually use to, get a handle on the concepts for your homework.
Exactly. Our mission here is basically to help you transition from thinking in just one dimension, like arithmetic, into the two dimensions of geometry. And the key insight, really, is that we need to get the language down first. Think of it like learning grammar before you write an essay. Definitions, terms, that's a foundation.
Okay, right, let's unpack this then. The whole idea of intersection is interesting even outside math, isn't it? Like where paths cross or, where your skills meet a need. But for geometry, we start simple. We start with angles.
Yes, and getting that language right builds intuition. It's more than just memorizing facts like a straight line is 180 degrees. You need to recognize angles by name. So if you memorize that a reflex angle is, say, between 180 and 360 degrees, you see it, you instantly know what it is. No calculation needed yet.
That makes sense. And that focus on language, on just knowing things, seems to apply to degrees and radians, too. It's not about heavy conversion calculations right now, is it? It's more about familiarity.
Precisely.
Like knowing water freezes at 0 Celsius and 32 Fahrenheit. You just kind of know both, right? So getting comfortable that 90 degrees is pi over 2 radians builds that same kind of gut feeling for scale. It makes the actual converting letter less intimidating.
That's exactly it. This groundwork, this memory work, it helps you develop a feel for what's reasonable geometrically. So later, when you do calculate something, you can look at it and think, yeah, that looks about right, or, something's off here.
Okay, so now this is where I think it gets really interesting. We move from geometry kind of floating in space, abstract ideas like parallel lines never meet,
Yeah.
to geometry pinned down on the grid, the rectangular grid, where everything has an address, a specific location.
Right, the grid is what makes it practical. It lets us turn those abstract ideas into algebra we can actually solve. Take parallel lines. On the grid, we can define them very precisely. They have the same slope, same m value.
Okay.
So, like $x plus 3 and $12x plus 4 week, they're parallel. And the cool thing about the grid is you can write down an infinite number of parallel lines just by changing that +3 to +4, though, the y-intercept.
Right, infinite possibilities,
Yeah.
but all sharing that same slope.
Okay.
And then the opposite, well, not opposite, but the other key intersection, perpendicular lines, they meet at a perfect right angle.
Exactly, 90 degrees. And the grid gives us this really neat algebraic trick for them. Their slopes are negative reciprocals. So if one slope is, say, 2,
Then the other one has to be in -1/2.
perfect. You flip it and negate it. And mathematically, the check is MBLE1 times MBLE dollars equals -1. That's the grid's way of saying 90 degrees.
Except for those special cases, right? Vertical and horizontal lines.
Ah, yes, the exceptions. Sigma 3 and Y's 2 for example. Their slopes aren't negative reciprocals in the usual way, but they're definitely perpendicular. Good catch.
Okay, so let's bring this right down to homework level. How does this intersection idea play out with inequalities, sketching and shading those regions?
Great question. This is a direct application. Let's use that example. 1, 5, 1, and 1 minus x plus 2, 2. Two conditions have to be met at the same time.
So 2 lines to think about, but one's greater than and the other is less than or equal to. You mentioned drawing them differently. A dashed line versus a solid one. Why is that?
It's all about whether the line itself is part of the solution. For non-angular none, the points have to be above y equals 1, but not actually on it. So we draw a dashed line to show it's like an open boundary,
Ah, okay.
not included.
Right. But for $x plus 2, 2, that or equal to means the points can be on the line $x plus 2, 2. So we use a solid line. It's part of the potential solution set.
So you draw the dashed line for y equals 1, the solid line for y equals minus x plus 2. Correct. And then you need the area that satisfies both conditions.
So above the dashed line and below or on the solid line.
Exactly that. You shade that region where the above y1 and below or on yx plus 2 interlap. That shaded area is the intersection of those two inequalities, visualized.
Okay, that makes sense. So wrapping this up, we've kind of journeyed from abstract ideas like intersection and angle types down to really concrete tools on the coordinate grid. Slopes, intersects, dashed lines, solid lines, stuff you can actually do to solve problems.
Absolutely. And as you practice this,
Yeah.
really focus on the why. Why that slope? Why dashed? Why solid? Why shade this region? Getting the process right, understanding the reasoning, that's what builds real mathematical discernment, much more than just checking if the final number is correct.
Right, the thinking behind it. So here's something to chew on. If the grid lets us define an infinite number of parallel lines, or perpendicular ones for that matter, What makes choosing the right line, the specific equation that matches a particular problem or a real-world constraint, the most critical skill of all?